Thanks so much, Christopher. I'm really excited after a very stimulating morning. And before I proceed any further, I want to give special thanks on the organizational front to David Mobley, who was responsible for a lot of organizing of SAMPL over the last few years, as well as Mike Gilson for allowing us to co-host this with D3R. So what is SAMPL? Well, technically, it means statistical assessment of the modeling of proteins and ligands, but that doesn't really tell you much. So we have to think back to, there is a lot of technologies right now, like free energy calculations, that are really exciting because on a well-defined, small, or possibly poorly defined, small domain of applicability, they seem to be encouragingly good in terms of performance, right? But when we look at the kinds of limitations that these methods face, I think this is everything I could remember about the FEP Plus tool, for example. We're of course removing limitations as time goes on, but there's a lot of different challenges that often occur simultaneously in treating real targets. And if you start to think about, how we turn something that's a research science that works some of the time on a limited domain of applicability into an actual engineering science where there's not a 2% chance you'll end up with a bridge if you start off on a bridge construction project, unlike starting to discover a drug, right? And you can design things like a plane in a computer, which is not going to fall out of the sky. You don't need to make 1,000 planes and then see which ones actually survive. It helps to think about how other fields made this transition too. So not all fields started as engineering fields. Bridge design, for example, was not very successful for quite a while. There was a single decade in the 19th century where there were 250 catastrophic bridge failures in North America alone. And they started thinking about maybe we should understand why bridges fail and what common modes of failure we actually see in the wild, and then try to make our models robust to those modes of failure. And I think that's kind of where we are as a field, at least in computational drug discovery. There's a lot we can learn from failure. So how do we maximize that learning? Now, the difficulty is when you see failure that looks like this, this is from Greg's paper, then it's really hard to make progress about, like, how do I go forward? In fact, as we did our first exercise in this, where we're trying to predict affinities to junk3 kinase, this is SAMPL0 in 2008 that was originated by Anthony Nichols. It's really hard to take this apart and really learn where I'm going wrong everywhere. And there's so many different sources of error that it's really hard to figure out how to proceed and how to get towards predicting quantitative accuracy. Now, fortunately, there's only a few ways in which things fail, at least for computational chemistry. Obviously, machine learning, it's going to have its own set of issues to worry about as well. Often the force field is blamed for not being accurate enough. We might be missing some essential chemical effects that have to do with like protonation states or tautomers, or we know that this is a huge problem, is that we haven't sampled all the relevant conformations either for the ligand or for the protein or for some other interacting partners. So the idea of SAMPL is to see if we can divide and conquer by isolating individual challenges, right? It's a companion to D3R, which is really trying to look at how well are we doing on pharmacologically relevant sets, and it's really trying to find stepping stone problems that isolate individual challenges that are challenges to quantitative accuracy. And we're hoping to provide targeted data sets as part of these blind challenges, and David will talk a bit more about the challenges of providing these targeted data sets with no budget, but at least the hope is to take these data sets, run these blind challenge exercises to focus the field on these important problems to make progress, and then to release targeted data sets that allow the community to actually progress. So nobody had really gone through and collected the steel tables that you need, under what stress does a piece of steel with a certain diameter and a certain composition actually fail? Like, it's a very boring experiment, but it's one that's necessary to turn a research field into an engineering field. And we also want to maximize the learning from these so that we can accelerate progress. This has had a long and storied history from the 2007-2008 days all the way through many different issues of JCAMD, through SAMPL5. They've typically involved things like modeling of simple protein ligand systems, hopefully simpler than kinase inhibitors, where we think we have rigid proteins, for example, that and very simple binding sites, or they involve computing physical properties where we can take the conformational sampling out of the picture, or host guess systems where, again, we can minimize the effects of conformational sampling on frustrating things. And David will talk about this tomorrow, but there have been cases where we started in SAMPL0 with doing hydration-free energies until we literally ran out of all the hydration-free energies that have been measured in the world. There's no more left and nobody's measuring them. Where we started with a lot of disagreement in these predictions, and at the end we could tell when the experiments were wrong because the theory was agreeing and was discrepant from the experiment. So just to give you an idea of what inspired SAMPL6 challenges, for example, Last year, we ran a challenge where Bas Rustenberg and my lab, a graduate student, went over to Genentech and measured a bunch of different distribution coefficients from between cyclohexane, which we think is much simpler than octanol, and water at pH of 7.4. And people did reasonably well, but one of the things that came up over and over again, and this is a graph from Frank Pickard's paper with Bernie Brooks, is that pKa corrections, when you add them, could be enormously large, even for this very simple transfer free energy. And it seemed like this could be a huge limiting factor in limiting our accuracy, even when we think we have a good force field and we've eliminated sampling challenges. And this is probably something that's relevant for protein ligand binding, because we've got all sorts of effects, like a change in the dominant ionization state, or a shift in the dominant tautomer, even if it doesn't change the charge, or even a population of a mixture of protonation states that would all cause predictive quantitative errors in actually figuring out how much this impacts binding free energies. And real molecules like imatinib do populate mixtures of protonation states at physiological pHs, and you can go into our wet lab. We took a ponatinib and did affinity assays looking at the actual binding, biophysical binding of this using fluorescence to DDR1 that came from Marcus Seeliger's group, and a small change in pH can give you a large change in affinity. So these effects are real for real kinase inhibition problems. If you try to survey these computationally, this was a survey we had done with Mariel and Gunnar, it looks like a lot of kinases binding to their FDA-approved inhibitors actually probably display some sort of interesting protonation state effects. And it's kind of pervasive. Everywhere you see color, there's some sort of effect that's predicted to go on here. So we think that protonation states are something we need to focus more on. So we've tried to cast several SAMPL6 challenges, which you'll hear more about this afternoon, one of which is now looking at how accurately can we predict small molecule pKa's, and that tries to just isolate how much are we impacting the chemical effects. We've, of course, returned with host gas binding affinities because these are fantastic systems that really isolate the force field challenges. And if you're at the right pH, you can eliminate the chemical effects and the sampling effects so that we can just see how well do the force fields work on drug-like compounds binding with protein ligand-like affinities. And then finally, this new challenge that Andrea Rizzi is going to talk about a little bit later is how well are we doing the sampling when we keep the force field and all the chemical states the same. So we're really trying to isolate each of these individual challenges so we can make progress as a field. And I have to thank Lyle Isaacs and Bruce Gibb. We'll thank the folks who actually did the measurements in their labs, but they've been a driving force behind SAMPL for many years, providing great host gas binding affinity data. Atep Isaac in my lab went over to Merck, and we have to thank these folks for allowing her to make a lot of measurements on the Sirius D3. And then Andrea Rizzi and Travis Jensen from Michael Schritt's group did this great sampling challenge. It's the first time we tried this, so everything is highly experimental, and we're curious to see what you guys think. And with that, we have next, Andrea is going to tell us a little bit about the host guest system. So if I can have him come up here.